Can you hear me at all? I can hear you typing. So I only heard feedback. I couldn't actually hear someone's voice. I can hear you typing, but I haven't heard your voice.
Stay muted. Yeah, stay muted. If there's feedback.
I could hear you for a second, but there was some feedback, but it might have stopped.
Should the audio be working now? Or should the audio be working now?
I think I heard someone's voice, but again, there was an echo.
Okay, we're still working.
Ah, that sounds better. The time lag is a bit weird. Yes, I can start talking. Can someone talk to me so I know if I can hear you? Yes, so I will log out so someone else can get ready.
for this work is my supervisor, Dr. Bruce Sutherland. Which contribute to ocean mixing, as you can see on the figure on the right. Because there are so many mechanisms, it's not very well understood. Lots of the current research has been focusing on internal wave breaking leading into turbulent mixing. You can see wherever there's a light blue line going to a gray squiggle on that figure, you have internal wave instability going into breaking, which is turbulent mixing. Comparatively less well studied is the inverse problem, which is turbulence leading to the generation of internal waves. So laboratory experiments have consistently shown that there is an excitation of internal waves by stratified turbulence. This excitation always happens at a pretty specific frequency. It's roughly about 0.8 of the buoyancy frequency, which is n, and this suggests a preferred wave selection mechanism within the turbulence. You can see that this frequency of about 0.8 of the buoyancy frequency corresponds to a roughly 45-degree angle from the vertical, which is shown on the figure on the right. Existing theories assume that these waves are generated at something which is known as the turbulent non-turbulent interface. This is shown as the heavy, solid black line on the figure. Throughout this talk, I will show through 3D numerical simulations that these waves are not generated at the turbulent non-turbulent interface, or TNTI, but rather they are generated within the turbulent region. So to initialize our simulations, the equations that we solve are the Boussinesq equations, where we have conservation of momentum, or Navier-Stokes, conservation of internal energy, and incompressibility of the fluid. The variables are listed on the right. For all of our simulations, we'll have the Reynolds number be 1000 and the Prandtl number be 1. A key parameter to focus on is the Richardson number, which will allow us to control the strength of our stratification through the buoyancy frequency n squared, as well as we set L naught and U naught to characteristic scales, a length and a velocity scale, by the initial shear layer profile, which is how we will generate the turbulence, which then proceeds to generate internal waves. The code that we use is known as Diablo. It's written by John Taylor, if that's a name that's familiar. It's a Fortran code which is parallelized using MPI. We initialize our setup as a channel flow. It has horizontally periodic boundary conditions, and it is vertically free slip boundary conditions. The time stepping uses a third order Runge-Kutta array for most terms, and then it's a Crank-Nicholson for the viscous terms. The domain size and the resolution are listed on the screen. So now that we have our code, how we initialize our simulation, we start with initial streamwise velocity, a streamwise background shear profile. We have this U bar, which is equal to U naught and 1 minus a hyperbolic tangent of Z over L naught. Setting the length scales U naught and L naught to 1, we then can think of our shear flow profile as being 0 above a certain level, and then it goes to being 2 below that certain level, thus the velocity varies with height. We superimpose one wavelength of the most unstable mode in all of our velocity components. The most unstable mode corresponds to the instability, which would be the fastest growing. And you can see that indicated on the vertical velocity there, where we have one wavelength of that most unstable mode in our initial vertical velocity. Now, what we also do is that we stratify our fluid later in time. We start with an initially unstratified fluid. So we take our initial Richardson number as 0, and we ramp it up over time. The reason for doing this is because a strongly stratified fluid will kill the turbulence. So we want to make sure that our turbulence is sufficiently turbulent to generate our internal waves before we actually stratify our fluid. We do this by the equation on the screen, where we use, again, a hyperbolic tangent profile, where we ramp up the Richardson number over time to some Richardson final over duration delta t around say, a time tr. This is shown for a Richardson final of 1, tr equals 50, and delta t equals 1, where you can see that we go from 0 to the Richardson number that we want very quickly in time. So what does this look like? So initially, we have the shear flow start to become unstable around t over t naught is equal to 20. That means the vertical velocity. So we have on the left the vertical velocity for a Richardson number, a final Richardson number of 1, and on the right, a final Richardson number of 10. The fact that these look the same is good because, as I discussed, the stratification hasn't actually started yet. As we proceed further in time, we definitely start to see instability around t over t naught equals 40. The simulations are still mostly identical. You can't really see any different because the stratification right now, which is the difference between the two simulations, has not really kicked in yet. However, as we proceed past that tr equals 50, so around t over t naught equals 50, we can clearly see a difference. We can see that the amplitude of the waves is stronger on the Richardson number 10 case. We can see that those waves have already propagated higher as they're faster waves. But the key takeaway is that the waves, while there are differences in their amplitude, the angle at which they are radiated from the turbulence remains identical. That angle is roughly 45 degrees from the vertical, meaning that the frequency with respect to the buoyancy frequency of these waves is at about that 0.8 that we expected to see from laboratory experiments. And as we proceed further in time, the waves continue to be released at that angle, and we can clearly see these waves being generated from the shear flow. So how do we analyze this? So we construct a horizontal time series at z0 equals 0, which would allow us to construct a power spectrum of the turbulent region. And we do the same for z0 equals 40, because that is where we'll be able to do this for the wave region. When we Fourier transform our time series to extract this power spectra, we'll call it P sub W because we just have the vertical velocity component in this power, and we move into wave number k and frequency omega space, we find, as we expect, the turbulence has a very broad-banded frequency spectrum, and the waves have one clear peak. If we extract a slice at a wave number of roughly 0.39, which corresponds to the most unstable mode, with U0 over L0 is equal to n equal to 1 for this simulation, we get a plot like this. So we see a broad range of frequencies in the turbulent region. We don't see really a clear dominant frequency or where it ever goes near 0. We contrast that with the waves, where there is clearly a peak frequency, and it's at that omega over n equals 0.8. This holds true for all of the simulations that I ran. This holds true that over a variety of Richardson numbers, where we go from, say, a Richardson number of 0.1 to a Richardson number of 1, regardless of our simulation stratification, we have a omega over n is about 0.85. So now we want to really dig into, we're seeing this behavior, we're seeing this wave frequency selection mechanism, it's replicating what we expect to see in laboratory experiments. How do we determine what is selecting within the turbulence these waves at this frequency? We use something known as dynamic mode decomposition, which is illustrated on that figure on the top panel. Essentially, you have the given fluid flow on the right, and you can decompose it based on its frequencies and extract, say, a dominant mode. On the left is the dominant mode for that dynamic mode decomposition example. So we can examine the structures of turbulence at the specific frequency that is extracted from that spectral analysis. So that will allow us to see exactly the turbulent structures which correspond to the generation of waves. In addition, we can use what's known as a Hilbert transform, which will allow us to separate the propagating components of our waves. We see it on the figure on the right from Mercier et al. We have a cross pattern of a flow, but when we separate it based on our wave number k, based on the sign, we can isolate a specific quadrant of that. By doing this, we will be able to determine which direction the waves are propagating and to verify if, as we saw in the simulations, that the waves are primarily propagating upward. So here's an analysis for the Richardson number final 1 case. We perform a DMD analysis, we extract the frequency at 0.85 n, and we perform a Hilbert transform to separate the direction of propagation. On the left, we have the initial DMD mode, which is selected at that frequency. In the middle, we have the downward propagating component based on the Hilbert transform, and on the right, we have the upward propagating component. As we expect, there's nothing in the downward propagating component, and the DMD signal is completely dominated by the upward propagating component. Now, another key takeaway is that these waves do not seem to stop at the turbulent-non-turbulent interface. Rather, these waves are generated from within the turbulent-non-turbulent interface. This means that existing theories that assume that the waves are generated at that boundary are not necessarily true, because these waves clearly are from deep within the turbulence. So, in conclusion, we examined internal wave generation from a stratified shear flow. We found that these waves were generated within the turbulence, not at the TNTI. The ongoing work is really focusing on determining energy diagnostics to figure out what exactly is going on with the turbulence. For example, we feel there could be a wave number interaction going on with the turbulence. This wave number interaction could possibly mean that there is a preferential transfer of energy between some of the wave number interactions in the turbulence to the specific wave number of the waves that get generated. This is all ultimately to build toward a theory to explain the frequency selection, building off previous work that has been done with coupling of, say, sound waves with turbulence. Thank you, and I'm open to take questions now.
Happy to take questions. And if you could repeat the question for the audience online.
Yeah. Yep.
Okay,
Thanks very much. It's a very interesting result. Do you know if this state the turbulence is generating internal waves? Is it a transition, or do you expect it to die away as the internal waves remove energy?
So the turbulence as a whole is actually decaying turbulence. So we do expect that as we proceed forward in the simulation, that the turbulence does sort of die off, and then the waves don't properly get generated because there's no more turbulence. But we are actually coding in a routine, a relaxation routine, which will allow the initial profile to always be what the velocity tries to reach, which then removes the problem of decaying turbulence, and we will no longer have any decaying turbulence, and then the waves can constantly be generated. And I know I was told to repeat the question, so,
okay.
Sorry.
I guess my question,
Yeah.
I understood that part, but
Sorry.
say you set that up.
Yep.
And so without the generation of internal waves, you would reach a statistically stationary state for the turbulence. You expect that the internal waves are not removing enough energy from the flow to cause a turbulence.
Yes, I would say the internal waves don't take enough to be the main cause of the turbulence decaying.
And I think that's really all we have time for in terms of questions. So thank you very much once again. And another round of applause. And our next speaker is online. And can you hear us, Francis? Francis, are you there?
Yes, I am here.
All right, we're just getting you set up.
I can hear you very well, yes. So you'll control the slides while I talk?
Yeah, I'm going to control the slides. We've had trouble with the screen sharing.
Yes. Okay, so I just closed the other tab and I can start anytime you like.
All right, well, feel free to go ahead. Francis Poulin from the University of Waterloo speaking to us about plankton blooms in the North Atlantic.
Okay, thank you very much for the introduction. And I should say this is work with a student, Andrew Watford, who recently finished his bachelor's degree in mathematical physics. The work that I'm presenting is something he's done over a span of 2 semesters as part of his honors thesis. And he will be starting his PhD in September at Oxford, working with David Marshall, I believe. Turn the page, please. So we can skip that. Next slide, please. Right. Okay, so could you go back one slide? One more? Yes, excellent. So for the motivation, I just wanted to give you a pretty picture and showing some of the biogeochemistry that the others have modeled in the ocean, and this is something produced by NOAA, and it shows different fields across the Atlantic. And I'm not going to be talking about this in general, but just wanted to give you an idea about some of the complexities that are going on. Of course, there's topography, which is important. There's wind, there's forcing at the surface, and lots of very complicated and interesting non-linear dynamics. And we'll be considering a very simplified view of this and trying to understand in a simple context what we can learn about these rather complicated models. Next, please. Next. So in terms of the particular numerical method or numerical model we're going to be using to study plankton blooms in the ocean, we're using Oceananigans, which is written in Julia, fairly new language, but has lots of fancy bells and whistles and aims to be very fast and friendly. So we're doing not a global model, but it can do that, but a regional model of the North Atlantic in the context of just a box, or a cube, I should say, when we do 3 dimensions. We'll include spherical coordinates, a non-uniform grid with 200 points in each direction. The model is hydrostatic, linear equation of state, anisotropic eddy diffusivities. We do run it on a GPU to get some fast performance. And in order to make things as realistic as possible in some contexts, we are using realistic data for temperature, salinity, and winds. And in the 3-dimensional model, when you show you simulations, it'll be after it's been spun up for about 100 years. Next. So this shows you the geometry of the particular region of the North Atlantic that we're interested in. I specify the particular range, and the depth goes down to 4 meters. The data we're taking are monthly averages, which we're using to force our model in the 3-dimensional context. And we have the temperature and the salinity is taken from World Ocean Atlas 2023. The wind forcing is from Copernicus Marine Surface 2023. And the particular gyre that we get in this context, as we'll see later on, is a single gyre. And I should say this is really building on a paper from around, I think, 12 years ago by Kuhn and Fennell. Next, please. Yes, so that was basically the physical model, but for the biogeochemistry, this is also by John Taylor, I believe. And there are a lot of different geochemical models you can consider. There are some very simple ones. There's some very complicated ones. There's a Julia library called Ocean BioME, which is short for Ocean Biogeochemical Modeling Environment, also in Julia, which is what we call an NPZD model. So it includes nutrients, phytoplankton, zooplankton, and detritus. And we essentially include the interactions between these 4 different compartments, which specifies the reaction, but the physics specifies how things are advected along, and the turbulent diffusion specify how things are going to diffuse in space. One important, in addition to the physical forcing, we need to specify the light extent and how that changes with latitude and how far it goes down in depth. And in some models, they allow for temperature variation of the growth rates and the grazing of the phytoplankton. And we'll investigate what effect that has on the kind of dynamics we see. Next, please. Next. Yes, okay, great. So before going to the three-dimensional model, Andrew spent a semester studying a one-dimensional model where it only includes a vertical column. And the simple test case we have here, a base case, assumes everything is isothermal. So say 12 degrees over this fluid column. And what's nice is that we do see what we expect to see, which is that on the right-hand side, we're showing how the nutrients, phytoplankton, zooplankton, and detritus change over a 1,000-day period. And because of the yearly forcing, we do see that there is a nearly periodic behavior. In terms of the plankton blooms, in the second row, we see that probably after maybe a couple of months or so, there is a phytoplankton growth. There is a little bit of a peak, as you may be able to see, and that peak then causes zooplankton to grow, which then causes detritus to grow, and things are complicated. By the end of the year, things tend to cool off, so the phytoplankton disappear, but then they come back the next year with an even bigger spike, and that seems to happen on a regular basis. So this is more of a proof of concept to see that our complicated model is producing what we expect to see. And I should say that it doesn't produce the spring blooms at quite the right time, which is something that is difficult to get right, but it does produce blooms that are at least close to the spring period, at least in this rather simple one-dimensional model. Next. And so this is showing the results, actually the differences with the base case of 3 different simulations. In the first one, we allow the mortality of the phytoplankton to vary with temperature. Second column, we allow the grazing of the zooplankton to depend on temperature. And in the third case, we consider what happens when both the mortality and the grazing depend on temperature. And as you can see from the second row, which shows the difference between these cases and the base case for the phytoplankton, the temperature, the mortality dependent on temperature does cause the phytoplankton to increase, more so than in the base case, which is the same in all 3. But what's more interesting is that in the third column, for the zooplankton, we see that because of the zooplankton mortality depending on temperature, we have that these zooplankton tend to die off more in the first case. They tend to grow more strongly in the second case because the grazing can be larger because of the temperature increases. But when we include both, we actually see a rather nonlinear behavior. There's growth early on, but then there's decay. Now, I can't pretend to explain exactly why these things happen, but I just want to illustrate that the complexity of these models is rather high, and they can produce rather different behaviors, and it's good to study them in a simple context so we can try to appreciate what they are actually doing. Next, please. And so that's all I'm going to say about the one-dimensional case. The rest of the results that I'll share with you are from the three-dimensional case. And the first case shows can't see it easily on the screen. So it shows the horizontally average buoyancy in the first kilometer over the spin-up period of 100 days. And because we start off with the state of rest, not the best idea, but the simplest thing to do, we do see that the mixed layer depth does increase, and it does seem to start to saturate. It hasn't quite saturated yet, but it is at least getting much more saturated than it was at the beginning. And on the right, we see how the vertical profiles of the buoyancy can actually change throughout different spans of the year because of the different temperature forcings above. Next. And so this is showing what the barotropic stream function, by that I mean the average stream function over the entire depth of the fluid, how that behaves how that behaves in terms of these. So it's averaged in depth, and I believe this is averaged over the last year. And we do see that there is a peak on the left, which corresponds to western intensification, and therefore means that we have a western boundary current. In this region, we would call it the Gulf Stream. Next. And so this is showing you on the left the horizontal profile of the velocity in the northward direction. And it's not the whole domain, just a subset. We do see there's a region of strong northward flow, which is again due to the Gulf Stream. And we see that it extends about almost, well, less than 1 degree in terms of longitude. And on the second profile, we see that there's a vertical profile, so it extends down to close to 500 meters. Next. And so this is what we end up getting when we take our complicated three-dimensional model and average over all spatial variables to give us basically a point at each time, which you could get very easily from just solving a system of ODEs. This is much more complicated, but it's something that you can compare with a simple ODE system to see how things differ. And we do see that there are phytoplankton blooms on the top right, which then corresponds to zooplankton growth. Again, we're not doing a quantitative comparison, just looking at the qualitative results. Next. And so this shows a vertical structure of the 4 different species as a function of time. And I want to draw your attention to the one in the top right, which is the phytoplankton. And we see that the phytoplankton bloom starts off very close to the surface. It does tend to descend a little bit. There is sinking of the phytoplankton, and that causes the zooplankton to grow and also the zooplankton growth to descend as well. Next. And I think this is the last figure I have for the results. So this shows a horizontal cross-section of the phytoplankton on the top left, zooplankton on the bottom left, and on the right we see the corresponding vertical profiles. And we see that the phytoplankton bloom starts off in the northeastern part of the domain, which corresponds to where we have upwelling, because it's the nutrients coming up in this corner that gives more food for the phytoplankton, then allows them to grow. And because of different processes I can't quite explain, we do have that then moves around and it does transition. There's a similar growth in the bottom, but not nearly as strong as it is towards the northern part of the domain. Next. And so this study has been a bit of a whirlwind tour, I know, but we've used some very powerful libraries that are out there to study biogeochemistry. And this is something that a fourth-year undergraduate student was able to do and started producing results in a span of 3 weeks, which I was very impressed with. And even though we found blooms, we like to ensure that we have blooms at the right times for the right reasons. And so this is going to require, first of all, looking at more data to see what is observed and try to understand if the models can actually produce those results. Thank you very much, and happy to answer any questions that we have time for.
Thank you for that, Francis. We have time for a couple of questions.
There was a question in the chat by Lisa. Should I answer that first?
Please do, and if you could read it out.
Okay, Lisa asks, maybe she missed something, probably not, probably didn't specify it, as to why I chose the region in the North Atlantic. Honestly, it's because the paper we were building on by Kuhn and Fennell, they studied the same region, and we thought it would be easier for us to start off by focusing on the same region, which then lets us to compare our findings with their findings. But their findings was from 10 years ago, so the data sets were quite different, and we wanted to look at more recent data sets to see how things have changed, but we haven't quite done that comparison yet. Thank you for your question.
Oh, we have one from the floor.
Unfortunately, I can't hear the speaker. I can't hear the question at all.
I'll summarize it for you when the question is asked.
Thank you.
So the question is that reaction diffusion equations often show pattern formation instabilities. Do you see those in your simulations?
We certainly do see patterns. I think I've shown some of them to you. In the context of research with a different student, we're actually looking at Turing instabilities that can occur. it would be nice to try to see whether that can occur in this very realistic context, but we haven't seen that yet.
Thank you very much. And I think we'll need to move on to the next talk. So another round of applause for Francis, please.
Okay, thank you very much for your time.
And our next speaker is Anatoly Poroshenko, who will be speaking to us about large-scale atmospheric circulation, energetics, and volcanic forcing.
Mm-hmm. Something. Yeah. Mm-hmm. Yeah. So thank you for the introduction. Yeah, today I would like to talk about helium cells and their power and energetics changes under volcanic eruptions. So let's start with the very beginning. As you know, we have sorry. Yeah, power is one of the parameters which can be used for estimate some influence, some impact of external forcing, like, for example, greenhouse effect. And according to some research, we know that there is a trend of increasing the power of helium cell. So for avoid and counteract this sorry, this what happens by greenhouse gases, we can, for example, use a geoengineering approach like injection of stratospheric aerosols. But before do it artificially, we should study it by naturally. So the natural injections are volcanics and they eruptions. So when sulfur aerosols reach the stratosphere, they affect to low atmosphere climate. In total they decrease quantity of incoming downward short wave irradiation and decrease the temperature of troposphere and energy which we have in troposphere also. So I would love to study helium cell by Lorentz energy cycle method. So exactly we will study a transition between available mean potential energy and mean kinetic energy. But the main problem of this approach, of this system of equations, that it's impossible to split contribution of each cell directly. So like you can see on the figure 3, there are 3 arrows, but if we want to study them separately, we need to find another approach. So, and it was suggested, it calls Carnot cycle method. So it exactly allows to study each cell separately. For this study, I used SMIP6 output from 3 models, CAN ESM5, MPI ESM, and Marek ES12. And 2 experiments was used. So background experiment was PI control, which helps to use Earth conditions in pre-industrial era. And I checked these changes using by 2 another experiments, describes Pinatubo eruption 1991, and strongest eruption which we have any data, it's Tambora eruption 1815. Yeah. And here you can see PI control cells. So we studied the winter cells for both boreal winter and austral winter. So for boreal winter, December, January, February, we studied northern helium cell in northern hemisphere. And for austral winter, we studied helium cells in southern hemisphere. Yeah, so the main part of this research is how it was calculated. So let's assume one air particle which flows through one streamline. So it means it makes a circle, and we can describe this movement in pressure and specific volume coordinates. And according to thermodynamics, we can calculate the net power of this movement. By the next step, we can expand not one air cell, but the air mass sandwiched between two streamlines. And knowing the difference between two stream functions of these streamlines, we can calculate a power generated by movement of these air mass. And after, if we know one loop, we can extend it for whole Hadley cell. So here you can see anomalies forced by eruptions. So non-dashed areas means significant changes on 95% level. And as you can see, temporal eruption makes much stronger and much more significant changes than Pinatubo eruption. So yeah, and here you can see changes in power in compare with the PI control experiment. So you can see bolded values. It means that we have significant changes in compare with PI control interannual variation. So you can see we have significant changes only for Tambora eruptions for Northern Hemisphere and not for all not for all models. So the same analysis was done for Southern Hemisphere, and the same. Again, Tambora provides more significant changes than Pinatubo, and the same result for the power calculations. Here you can see that we have much more significant changes in power. For example, we have one experiment for Pinatubo for first year, and all experiments for second year for Tambora, and 2 out of 3 for first year after Tambora eruption. So in conclusions, we have the stratospheric high resolve forcing. It contributes significant changes, especially for Tambora eruption. And another important, we have opposite trend in compare with greenhouse gases effect. So increasing for greenhouse and decreasing for volcanic eruptions. So thank you for your attention.
We have lots of time for questions. Well, I'll ask a first one. Have you looked at the feral or polar cells as well to see what kind of?
So it's for continuous research. I do it in drafts, but not for presenting. But as you can see, for significant changes, we can see significant changes for both winters. So here, especially for Tambora eruption, and for feral cell for astral winter. So we have significant changes, and probably it can give a chance that we will have significant changes in power in future research.
Any other questions?
I guess just a general question. Is the eruptions are in the northern hemisphere or the southern hemisphere?
As I remember correct, Pinatubo eruption, it's northern hemisphere, but it's pretty close to tropics. So we can say we prefer to divide like tropical eruptions and extratropical eruptions. So they both were tropical eruptions, but Tambora probably southern and Pinatubo more northern hemisphere.
So were the effects equal in both hemispheres, the power decrease?
As you can see, yes. Yes, so yeah. It's pretty same result. So here the more important that Tambora eruption was more powerful one and injected much more sulfurs into the stratosphere.
I'm just curious, how long do the effects of the decrease in power due to these?
It's usually so for Pinatubo, we can see that second year already non-significant, but it's usually according to temperature plots, it's 2 years. So in power, I think we can estimate something like this. 2 years probably for Tambora, just because it was much stronger, probably 2-3 years.
Well, it's another question. It's my own unfamiliarity with some of these metrics, but the rate of power production in the various circulation cells do those scale with things like precipitation rates and the rising branches, or is that a naive? Well, if I want to relate, say, power to something which is more directly observable, like precipitation rate, is there a simple connection between?
I cannot answer right now because so I need to study more this equation. Yeah, because I worked exactly with stream functions, not with precipitations.
Thank you very much. Well, we have a few. Oh, yes, another round of applause. Thank you. So we have a few minutes until the next talk, and I want to make sure that we stay on time. So we're going to just take a break for a few minutes, and our final presentation will be at 2:30. And just to get ready for that, Yu Cheng, are you online?
Do you hear me? Do you hear me?
We can hear you. Can you hear us?
Yeah. Can you hear me? Hi. Can you hear me?
Yes, we can hear you, and we'll start
Okay.
in a couple of minutes.
I can share my PowerPoint by myself.
No, that's actually not working. We haven't figured out how to make that work. So what we'll do is we'll show the PowerPoint on this end, and you can just please let me know when you want me to change the slide.
Okay. It's okay. It's okay.
Let's just give it 2 more minutes so we stay on schedule, because some people might be joining us online at 2:30.
Okay.
Well, I guess it's getting pretty close to 2:30, so we can get going.
Oh.
So Yu Cheng, please feel free to start speaking whenever. And just to let people know, our speaker will be Yu Cheng Zi, who will be speaking to us about the southern stratosphere warming events in the Antarctic in 2024. So.
Okay. Thank you. Hello everyone. I'm Yu Cheng Zi from as a visiting PhD student from China. Now I study at Dalhousie University with Jin Yishen and the BIO with Zheng Xiaolong. Today I want to talk about the southern stratosphere warming events in the Antarctic in 2024. Next. First background. Next. Okay, southern stratospheric warming is SSW is a significant warming phenomenon in the stratosphere and the mesosphere in wintertime, with a sharp increase in temperature in a week and 2 weeks. So SSW have important as troposphere extreme events. So which is important precursor for the extreme acute events in the troposphere. In Arctic, it's average 610 per 10 years. However, it's in the Antarctic, it's average 1 to 10 per 10 years. So it's few SSW in the Antarctic. Just in the 1988 and 2002 and 2019 year. Next, thank you. And data and method. Data including EI5 analysis, reanalysis, and MEL2 reanalysis, and so on. And the methods include AP flux and AD heat flux and the field analysis. Okay. So, And the second is characteristics of the Antarctic SSW in 2024. Left panel, panel A is a time series zonal mean temperature at 16 to 19 degree latitude, south latitude at 10 millibar. And the panel B, red panel B is a zonal mean zonal window at 10 millibar. And bottom panel is a distribution of the potential vorticity PV at 10 millibar. As we all know, in the July, Antarctic stratosphere is at its coldest and strong SPV is a stratospheric polar vortex, and during this time is has to disturb. However, in the July to August 2024, consecutive SSW events in occurred with warming more than 17 degrees. And July SSW occurred at the earliest winter time of the year, recording in the Salt Lake era since 1979. August SSW, the SPV weakens and significantly strengthening. Next. As we all know, and planetary wave is the main causes for the SSW. So we use the epiflux to diagnose the planetary wave. Left panel is epiflux and its convergence anomaly. And the panel C is epiflux divergence at 2 millibar. We can see before the July SSW and the strong planetary wave upward and convergence in the stratosphere. And in the panel C and the July next, the convergence of epiflux at 2 millibar was more than twice the historical maximum. So it's very, very extreme. And before the August SSW, the multiple planetary wave also occurred. Next. Okay, next. Okay, a third is causes of the Antarctic SSW in 2024. Okay, this is effect of blocking height and the SSW. Blocking height can trigger planetary wave in the troposphere. So this panel is distribution of geopotential height anomaly at 215 millibar. Left panel is total wave, and middle panel is wave 1. The red panel is wave 2. Is for the 4 data. And before July SSW events and the July 7th, in the 3 blocking height over the South Indian Ocean, Southeastern Australia, and South Pacific formed the wave 2 pattern. And the July 13th, the blocking height just only the South New Zealand shift eastward intensify and lead to the wave 1 pattern, and wave 2 is too weak. And before the August events in the 26th July and 4th August is blocking height over the South Indian Ocean and the South Pacific, and the contribution to the wave 2 pattern. And the wave 1 is too weak. Okay, next. This is a time series of geopotential high amplitude of wave 1 and wave 2 represent the intensity of blocking height. So we can see the before the both SSW wave 1 and wave 2 show multiple strength peaks, and with wave 2 amplitude near historical record in the panel C, and indicators indicating the strong blocking height can trigger extreme planetary wave in the troposphere. Okay, next. Okay. So second is effect of CIS loss in the Amazon and the Ross Seas in Antarctica. And the panel A is time series as extent, and the yellow line is climatic mean. Green line is 2023. Red line is 2024. And different gray shading is the maximum to minimum and 10 to 19% and so on. And panel B is S extent anomaly, and panel C and panel D is distribution of the CIS concentration in the 2023, 2024. We can see panel B in the 2024. CS can continue to the loss with the extent second only to the 2023. But and in the July, significant C loss was was in the Amazon and the Ross Sea. However, but in the 2023, the CS is increasing in this region. So it's opposite in the 2023, 2024. Next. Okay, we did the correlation with June CS concentration with the July August temperature and in the 10 millibar in panel I and panel J, and panel H is June CS concentration and the SLP anomaly in the 2024. And bottom panel is time series CS concentration and temperature in the July August at stratosphere. We can see the July to August stratosphere temperature over polar region show a significant negative correlation with the June CS concentration, and in the Amazon and Ross Sea, with the correlation coefficients reaching the negative 0.4, and we can in the panel H, we can see positive SLP anomaly over the Amazon and the Ross Sea. So the continued CS loss in 2024 can maybe have created favorable condition for the development of blocking high. Okay, next. This is a stratospheric preconditioning for the SSW. This panel is added heat flux at 10 and 100 millibar. We can see a panel B is in the 100 millibar. Planetary wave approach the historical records. However, in the panel A and the 10 millibar, it was twice the historical maximum, indicate a significant application of the planetary wave in the stratosphere. So, stratosphere maybe exert some prediction effect, result in significant application of planetary wave at stratosphere. We can call the wave resonance. Okay, next. Next, we can use the meridional potential vorticity. Vorticity is PV. PV gradient to diagnose the stratosphere precondition, which is part of the planetary wave refraction index. In the we can up panel is time series meridional PV gradient at 10 millibar. And the bottom panel is a distribution of PV in the 21 June and 31. We can see under June 30 to July 1st, the gradient exceed historical records and indicate a significant modulating planetary wave. And in the bottom panel, we can see the stratosphere condition lead to the mixing of PV towards the polar region, which is an irreversible irreversible process that disturbs the SPV. Okay, next. Okay, next. Okay, it's finally the change in ozone and the impact. Panel A is a time series of daily total color ozone, which is TCO3. During the July SSW, TCO3 increased significantly and approached the historical level in the panel A. And before the August SSW in multiple planetary wave and enhance powered also transporter and keeping ozone higher levels. And as we all know, ozone can absorb the short wave radiation and hit the stratosphere and creating very favorable condition for the August SSW. And it's interesting in the panel B, which is time series monthly TCO3 in the July, and from different date set, EA5 and MIR2. We can say TCO3 is highest in the July 2024 since 1980. Further highlight the extreme nature of planetary wave during these two SSW events. So indicator this SSW events is so many extreme. Okay, next. Okay, is the conclusions. In this paper, we did introduce the July to August 2024 SSW events in the Antarctic and blocking high and CS loss in Antarctic and stratospheric preconditioning, and also transporter playing the important role in the SSW. Okay, that's all. Thank you. Next.
Thank you very much. And we have time for one or two quick questions. Are there any online?
Okay.
No questions online. I have one quick question about your final point regarding the increase in the polar ozone.
Okay.
Is that simply a function of a larger amount of transport of ozone into the high latitudes from the mid latitudes, or is it a change in the temperature of the polar vortex and therefore changes in the production of ozone consuming catalysts?
Oh yeah, it's good question. I think ozone transporter make a part of the role in the sun warming. I think SSW. I think planetary wave is the main causes for the SSW.
Okay, thank you very much.
Okay. Okay.
And that wraps it up for this second session of Atmosphere, Ocean, and Climate Dynamics. I'd like to thank all of the speakers once again. And have a good rest of the afternoon.